So if we concede that all measurements are at some point estimates, and our goal is to just get better and better estimates with better and better measurements, let's take a second to talk about the vocabulary of discussing measurement error and uncertainty. So the first two terms we want to tackle here are the idea of accuracy and precision. These are technical terms that are sometimes used interchangeably, but when they're talking about measurements and specifically groups of measurements, then we're very clearly talking about technical concepts here. So accuracy. Accuracy is how close you are to your intended measurement. Sometimes you're doing experiments and there's no way to verify what you should be getting. Other times you are doing lab work or experiments to verify a certain concentration of a substance or an ability to absorb a particular wavelength of light. And so we often know the target we're shooting for, and our experiments are verification type experiments. Accuracy is how close you get to that known or accepted value. So to be accurate, and this is often the image you'll see is some kind of a target image, darts, archery, that kind of thing. And so if you look at the target board here, accuracy is hitting the bullseye. Precision is about grouping. Precision is how close all of your measurements are to one another. So if you look at the bottom left corner of this diagram, you can be extremely precise, multiple measurements in the same spot, but inaccurate. This might happen if your balance is not calibrated. So you would be weighing objects that would all be too light or too heavy for the expected mass, and yet they would all be close together because your technique is still fairly consistent. You can have a lack of precision but accuracy, but only if you're dealing with a group of measurements. Because often what we will do with a group of measurements is we will find an average, and it's possible for you to be off in either direction in such a way that the average of all of your measurements is fairly close to your intended value. So the top right corner of this diagram shows you accuracy in the average, but a lack of precision. No individual measurement in that top right corner would be considered an accurate measurement. And then you can have scatter all over the board, nothing coming anywhere near the bullseye. That would be a lack of both accuracy and precision, and that is a clear sign of poor experimental technique. Side note, the term precision is a bit, imprecise. What do I mean by that? Well, it depends on whether or not you're talking about a single measurement or a group of measurements. Oftentimes you will hear someone talk about a measurement or a measuring device having high precision, meaning it can measure a thing out to a lot of significant digits, or sometimes we're just going to be looking at decimal places. If you have multiple iterations of the same measurement, though, precision is only about the grouping and not how many decimal places you have. So be careful of the context when talking about precision. There's two other things we want to talk about with respect to error, and those are the two types of experimental error. The first type of experimental error is called random error. Random error is the error inherent in all measurements, and we refer to it as random because it could be either high or low. When you are making an estimate, every time you measure, you are just as likely to estimate low as you are to estimate high of the exact value. And it turns out we don't ever get to know the exact value. And 100% certainty of the truth of a measurement is not the goal of science because it's unattainable. What we can do is get better and better measuring devices, and we can get better and better at measuring. And we imagine that we're assuming that we're getting closer and closer to that true value, generally through communication throughout the scientific community, confirming one another's work. Random error is inherent in all measurement. It's just as likely to be high as it is to be low, and it can generally be reduced by multiple iterations. This is why you never just do one trial of a particular experimental process. You're going to do multiple trials, and the hope is that all of those values are repeatable. Which brings us to our last bullet point here. There are two, again, similar concepts that have technical meanings within science. Repeatable is the ability for a single experimenter to get the same value through multiple trials of the same process. Reproducible is the ability for someone to take that experimental work, recreate it, and get the same results. And these are two linked and important concepts in science. Examples of random error. For instance, you might have an inability to control all the relevant constants in the room. A very sensitive balance, for instance, will pick up air currents in the room. And if you're measuring things that are very light, you'll get a lot of fluctuations. So you'll see really sensitive balance actually built with glass cages around the balance pan to minimize that form of random error. But those air currents are just as likely to increase as decrease the measured mass value. And then again, just the fact that all measurements are estimates. What we can do is get better and better measuring devices so that those estimates are on a smaller and smaller scale. And that's in the last couple of videos where we've looked at increasing the number of marks on a measuring device. All right, our second type of error is called systematic error. Systematic error is a flaw in your experimental design or execution. You cannot reduce experimental error through multiple iterations because every trial is going to have the same error. A good example of this is a balance which is not calibrated properly. So I think we talked about this at the first picture, right? If all of your values are weighing too heavy because you have a poorly calibrated balance, no number of times of doing that is going to get you the lower value that's going to average out to give you accuracy. Some other examples of systematic error. Errors in the measurement of temperature due to poor contact with a thermometer and the substance that you're measuring. So most thermometers are designed to be submerged in a fluid. At the very least, like a meat thermometer is designed to be submerged within cooked meat. And so if you're just touching the surface, you're unlikely to get that internal temperature, or you're unlikely to get the temperature of the liquid if you just touch the thermometer to the side of the glass. So not using an instrument properly. If you were trying to measure solar radiation, but you had shade over the course of the day that was covering, like you just left, a radiometer is going to measure the amount of heat coming from the sun. If you left it out on a flat surface, but over the course of the day, shadows kind of moved over it, that is a poor experimental design, and that's going to give you fluctuations in your readings. If you don't set an instrument to 0, so it's not measuring properly, again, it might measure high, it might measure low. Calibration is really, really important. In commercial labs, most of the equipment has what are called calibration dates on it, and they have to, throughout the year, record the process of calibration, sometimes hiring companies to come in whose only job is to calibrate scientific instruments. One last little note on accuracy and precision. If you minimize your systematic errors, you are likely to generate high accuracy. By this we mean if your experimental process is clear and coherent and valid, you are likely to get really accurate results. Small random errors lead to high precision, and we generally reduce random errors by the sensitivity of our measuring devices, using a meter stick marked to millimeters rather than a piece of yarn that had been measured off to be 1 meter. You're going to get better measurements of length, and you're going to have high precision. And so that kind of summarizes the ideas of experimental error. Be sure that you are clear on the ideas of accuracy and precision and random and systematic error.